Good evening. Today is the sixth class of fluid flow operations. This week we have learnt about mostly friction losses and uh, head losses, friction factor, kind of how the bearings, how the pumps are having the friction losses. Okay, so we'll discuss that. We'll start in 1 minute. Okay, I'm sharing the screen first. Okay, let's start discussing the things. So we know the Bernoulli's equation, right? So generalized Bernoulli's equation form was like this. If you remember the expression, it was P1 by rho plus alpha 1 V1 square by 2 plus GZ1 plus eta rho P, that is the work efficiency, equals to P2 by rho plus alpha 2 V2 square by 2 plus GZ2 plus HT, right? So suppose this is happening in a same plane, okay? This is happening in a same pipe. So there will be no GZ term, okay? This will be 0, this will be 0, and the fluid is stationary also, so it doesn't have any velocity. So this term will be also 0, and we are not doing work, so this is also 0. So what is left? So HT is P1 minus P2 by rho. So this is your head loss term, okay? Or and this head loss has two components: major head loss and minor head loss. So we represent it like H major and H minor, okay? So now what is this H major? H major considers the friction in straight pipe. Friction in straight pipe, and major loss and minor loss. So this is H major is major loss, and this is minor loss. And this minor loss is happening due to bends, valves, fitting, sudden expansion, etc. Okay. Okay. So this is a basic concept of head loss, total head loss. Now, how do we represent? Like where these things are, like energy is lost or head is lost basically. So suppose there is a pipe. They have same exposed surface. This is minorly curved. Okay. And now we have made the exposed surface more rough. Okay, like this. So friction will be more higher in this case, and that will lead to more head loss, right? So suppose you have learnt about the Buckingham Pi theorem, right? In your other courses. So Buckingham Pi theorem is basically to represent in dimensionless numbers. So represent your work or your system in dimensionless, a set of dimensionless numbers. Okay. So we'll do now, like suppose delta P, that is the pressure difference. This is a function of, like, if you remember your pipes, like a fluid is flowing through a pipe and there is a pressure drop. That is why the fluid is flowing. Then like on which parameters this pressure drop will depend, right? So it will depend on the channel length, right? If channel length changes, the pressure drop will also change. So it depends on channel length, that is L. Next, it depends on the fluid velocity, right? The pressure drop will change along with the fluid velocity. Similarly, it will depend on the diameter of the pipe. Next, it will depend on the density of the pipe, right? Like oil have a different pressure drop in the same channel, but water has a different pressure drop in the same channel, right? Then viscosity, very obvious. And then there is a E factor. This E is called the roughness parameter. Everything else this term is new. This is the roughness parameter, right? Next, so in Buckingham Pi theorem, like how will we decide that what number of dimensionless group we will create? So here there are, if you can see, there are 5 variables, right? 1, 2, 3, 4, 5, 6, and this, sorry, 7 variables, and this delta P. So total number of variable is your 7, right? Next, and there are fundamental dimension, that is 3. What are fundamental dimension? That is your M, L and T. That means mass, length or distance, time. These are your fundamental dimensions. We are not considering there is another theta, we call this temperature, but we are not considering it now. Okay. In general, the fundamental dimension is 3. So now N minus M is equals to your number of dimensionless groups. So here it will be 7 minus 3 equals to 4. So we will have 4 number of dimensionless groups which will be relevant to our system, right? So now we'll see what are these numbers. Suppose in these terms we are setting up like this. So there is delta P. So we can take two terms like right, rho v square. Suppose we are taking this, right? And how much way you can functionalize it? We can functionalize it like dv rho by mu. All the terms are of function. You have seen in the previous slide that all of these are under the delta p, right? So you can represent this like this: L by d and E by d, right? Now these terms we know, and that is why we are predicting this. For your system, it may be different. For different systems, actually, these dimensionless numbers will change accordingly, and you have to be very careful before defining that. Okay. So in pipe case, what we want to know? We want to know the roughness parameter. That is why we are scaling it. We want to know the length scale, like how this length and diameter are varying. So we are defining L by D. We want to know that how much fluid velocity, and we know that Reynolds number is controlling that, right? It will tell you about the laminar or turbulent flow. That is why we are defining Reynolds number. And there is another term, that is your delta P by rho V square. That is your energy terms. Okay. So we know that delta P by half rho V square is defined as the top one is the static pressure drop. Excuse me. And bottom one is the dynamic pressure drop. Right? So, and we have seen previously that delta P by rho is the major head loss. Delta P by rho is the major head loss. So now how can we define this? So if dV rho by mu is Re, then E by D, then L by D, and there is a V square by 2. So we are multiplying it with V square by 2, right? So in the experimental observation, like when we do experiment, we have seen that this Reynolds number is related to the roughness, because you have seen in the previous slide that if the channel is smooth like this, there is less chance of chaotic fluid motion or chaotic fluid flow, right? It will be more streamlined, right? But in here, it will be more streamlined like this. It will more likely to go layer wise, right? But in this case, as there are many rough factors or roughness factors, and there is physically boundaries are present, and all these things are very rough. So what happens? There is little chance of mixing at the side, because everywhere the fluid tried to go, they will find a obstruction. So there is a high chance of little bit mixing at the corner side, right? So that will lead to more chaotic motion. Chaotic motion means turbulent flow. So this is defined. So that is why they are saying that this RE is somehow related to this roughness factor, right? So now we can write it similarly like phi REED together, and then there is LD and V square by 2, right? Now this is your FD, L by D, V square by 2, what you are studying, that it is the major head loss in the lectures. So this FD, this FD is your Darcy's friction factor. Darcy's friction factor, and there is one FF, which is your Fanning's friction factor. Fanning's friction factor. And how these two are related? These two are related like FD equals to 4 into FF. That means Darcy's friction factor is the 4 times Fanning's friction factor. Okay. So now this del P by rho is 4, like earlier it was FD L by D V square by 2. Now it is 4FF L by D V square by 2, right? So this is the delta P by rho, and this is your major head loss. So in the previous case, or in the earlier class, you have seen about the Hagen-Poiseuille equation, right? So if you remember the expression of Hagen-Poiseuille equation, so what it was saying, so Hagen-Poiseuille equation is talking about the flow rate inside a pipe channel, right? So flow rate inside a circular pipe channel, viscous flow rate, right? So where the flow rate expression was like this: Q equals to pi d to the power 4 delta P by 128 mu L. So these things we have done in the earlier classes, that how this Q is flow rate is coming. This is your flow rate, right? Mass flow rate. Now Q can be written as V into A. So A means the area of the pipe. So what it is? Pi by 4 d square, and this is V. Like V is the velocity, equals to pi d to the power 4 delta P by 128 mu L, right? Now what it is coming? So delta P is coming as, if you remember, pi will cancel out these things, 1 square is left, right? And 4, this is 3, 2, right? So delta P is your 32 mu LV divided by d square. This is a pressure drop equation in the circular pipe channel of a viscous fluid, right? Now, if you want to divide it with delta P by rho, divided in the density, we want to calculate the major head loss. So delta P by rho means this will be divided by rho. 32 mu L V by T square rho, right? Now, if change it, like if you just rearrange the terms, what it will come? So, you can, first I'm writing and you can see that. 64 by D V rho by mu L by D V square by 2. So we want to write it in the major head loss term. So major head loss term was like that, right? There is another term. There is in the right hand side there is L by D and V by 2, V square by 2. So, and if you want to write like this, you have to take this, as we are dividing this whole thing by 2. So here it is coming 64. 1D has come here. There is one V is in the bottom and there is rho, and the top mu is coming to the down. So this is very known term, right? What is 64 by RE L by D V square by 2, right? So now if you compare with this major head loss term here, so this is exactly same, right? This is exactly same. So now we can say that this Darcy's friction factor, if D is 64 RE, right? And now we have seen that Darcy's friction factor FD is 4 into FF. Then what it is FF? So FF will be, fanning friction factor is 64 by RE by 4. So it will be 16 by RE, right? So these are the basic expression you should remember for solving very simple questions or MCQ kind of thing, or maybe these are very important in GATE question also, right? Remember this, right? These are for like laminar flow. This expression is defined for, because Hagen-Poiseuille equation is also defined for laminar flow. And for turbulent flow, there is a Moody's chart. For turbulent flow, we calculate these things from Moody's chart. So I'll show you the chart. Yeah. So if you see this, yes. So this is a very famous very famous diagram of Moody's diagram. These are called Moody's diagram. So it is the diagram of Darcy friction factor, that is FD versus Reynolds number curve, right? So this gray zone, I think my screen is visible. So this gray zone is the laminar zone, okay? Then this yellow zone is the transition zone, and this zone, this turbulent zone, or this orange zone, is the turbulent zone. So this line is for hydraulically smooth pipe, which is not the ideal case, right? Which is the ideal case, but in reality it is not the case. And this graph is for hydraulically rough surfaces, rough pipe. Okay. So for turbulent cases, we will calculate this FD from this chart, or for laminar case also you can calculate. But for this turbulent flow, this FD is very important, right? Okay. Going back to the session. So this is your Moody's chart. So you have remember what is the friction factors, and there are some empirical equations of friction factor and friction factor and like Moody's friction factor and the fanning friction factor what sir has taught. These are some empirical equations. So while solving the problems of our assignments, we will go back to these equations. Okay. So let's start the solving equation. So in turbulent flow, losses are proportional to viscosity. Is it true or false? In turbulent flow, losses are proportional to viscosity. Is it true or false? Tell me. So let's go back to the notes. So here here comes the frictional loss. So during fluid flow through conduit, the energy is lost due to frictional resistance. It is called frictional loss. In laminar flow, losses are proportional to fluid velocity, and in turbulent flow, losses are proportional to square of fluid velocity. Right? So this is where your answer lies. So it will be mu square, right? So here comes the Darcy, Weisbach and Fanning's equation. So just now we have seen that how this is coming from the Bernoulli's generalized equations. So H is the pressure gradient by rho g. Okay, so here comes, you can see that how rho v square by 2 is divided. This is the Darcy friction factor or Darcy-Weisbach equation. This is your expression, right? So you have seen that Darcy is the 4 times of Fanning's friction factor. So this is written like this, right? This is the same thing. So this is the Darcy expression. This is your turbulent flow expression. The turbulent flow, we know V star is the we have learned in the last class that turbulence for V star is the root under tau 0 by rho, and this can be written by like this from this expression, right? So universal friction factor for turbulent flow through smooth pipe. This is the expression. Okay, this is the FD expression. This is an example around that. This is another example. Please go through the examples to solve by on your own. So here the old pipe roughness has been calculated. How these are calculated? The first one is the epsilon expression is the epsilon old equals to epsilon new plus alpha 80. This is the equivalent roughness height of old pipe. This is the roughness height of new pipe. And this is the number of years. This is the constant. Alpha is constant, can be found by experiment, which varies with pipe material. Okay. So using this expression, they are solving a problem. Now this one is the Kohlrausch empirical equation for friction factor, what I was telling. So it is 1 by root f equals to 1.74 minus 0.868 ln epsilon by r plus 18.7 by re root under f. Okay. So this is an empirical equation. You have to remember this. There is a problem around that. This is the Blasius empirical. So last one is the Kohlrausch correlation, and this one is the Blasius empirical equation. So this is the friction factor. And what is this expression? This like 4 tau 0 by rho u square by 2. Okay. Lee's empirical equation is like this. You have to remember because MCQ may come from this. Okay. This is the Schiller and Harman empirical equations. Okay, you have seen that slightly the numbers are changed everywhere. Okay, right? This is the Nikoradze empirical equation. So everything is same. You can see the expression is same, but the numbers, the power of RE is changed little bit everywhere. So these are all empirical equations which has been developed from the experimental factors. Considering the experimental factors. Okay, so that is why they are little bit different, but the overall thing is same. This one is the Moody's empirical equation. And that from where the Moody's chart has been coming. Okay, this is the friction factor for transition flow between the laminar flow and turbulent flow. Okay. Now going back to the question. So in turbulent flow, losses are proportional to viscosity square, mu square. Next, the fanning friction factor for laminar flow through a circular pipe is given by this. Which one? So we have seen the fanning friction factor, right? So fanning fraction we have just calculated. So Darcy friction factor in laminar flow is given by 64 by Re. So fanning friction will be 1/4 of that. So it is 16 by Re. What is the fanning friction factor if Re is 1600? So just now we have seen the expression of fanning friction factor. So it is 16 by Re. So 16 by 1600. So it is coming 1 by 100. That means 0.01. Next, a fluid is flowing through a pipe of diameter 30 centimeter and 20 centimeter at the cross sections A and B respectively. The velocity of fluid at section A is 5 meter per second. Determine the velocity at head B. So velocity head we have known like this, right? Okay. So we have seen earlier in the last class A1 V1 equals to A2 V2, right? So A1 is the area at the A point. So this area is coming as, you calculate pi by 4 d square, right? So pi by 4, 30 centimeter it is written, so it is 0.3 square. Velocity is 5, right? And A2 is pi by 4, 0.2 square, and we need to calculate this VB. Okay, so how much it is coming? Calculate on your own and then check with me. Everything is written. So VB will be 0.3 square into 5 divided by 0.2 square equals to 11.25 meter per second, right? And now this velocity head is coming from the same Bernoulli's equation, right? We have considered that major loss because there is no flow, there is stationary fluid. That is why V1 square by 2 term has been cancelled out. But here there is a flow is happening, so we have to consider the term. So this is our velocity here. So this is the velocity head is VB square by 2G equals to 11.25 square by 2 into 9.81 G, or here it is written as 10, so 10. So it is coming as 6.328, right? Which is near to this option A. Next, consider a highly corrosive Liquid is flowing through a pipe of roughness 0.05 millimeter. Due to current pandemic, the pipe was unused for 150 days. As the workplace opened, it was noticed that the roughness of pipe was 0.01 millimeter. Now the owner of workplace wants to use the same pipe for another 3 years. In such condition, what should be the roughness of the pipe? Okay, tell me. So it will lead you to this equation. So initial roughness was 0.05, right? And after 150 days, the roughness become 0.1 millimeter. And then also you want to use it, right? Just a minute. So you can calculate this. The equation was Kt equals to K0 plus alpha T, right? It will be 0.1 millimeter because the roughness has increased, right? It will not decrease. So now at what rate it will change, we have to notice. So Kt is 0.1, K0 is 0.05 plus alpha into T is 150 days. 150 days okay, so alpha is 0.1 minus 0.05 by 150, that is 0.05 by 150. How much is coming? 3.3 into 10 to the power minus 4. 3.33 into 10 to the power minus 4 millimeter per days. This is the rate. And now with this rate you want to use it for more 3 years, another 3 years. So 3 years means 3 years into 365 days per year. So it is total 1095 days, right? And this linear growth now will be happening, like K final will be the final. So K initial now is the 0.05 plus alpha is 0.05 by 150 into 1095, right? How much is it is coming? So it is coming as 0.415 almost. So in the expression, the nearest option is 0.33. Okay. It will always be less because it may be leap year or something. So it will be not overestimated. It will be underestimated. So this is 0.33 will be the right answer. Okay. Next. Um, Blasius empirical equation for friction. So we have to now compare. Okay. Compare it. So we have seen some empirical equations right now earlier, right? So how this is, so Blasius equation, in Blasius empirical equation, the RE varies from 2300 to 10 to the power 5. So A is related to 2. A is related to 2. Less empirical equation for friction factor varies from 4000 to 10 to the power 4000 to 4 into 10 to the power 5. Schiller and Harman equation varies from 2300 to 4 into 10 to the power 5, and Lippert's empirical equation varies from 10 to the power 5 to 10 to the power 8. So it is A2, B4, C3 and D1, option C. Okay. Next. The loss of heat due to sudden expansion of pipes given by what? For sudden expansion, it is given by HE equals to U1 minus U2 whole square by 2. Okay. So this is option B. Next. The loss of heat due to bends in pipe depends upon the loss of heat due to. So this is, the option is all of the above. I think there is a printing mistake, but you can give all of the above, right? Let me check again. Next. Which one of the following does not cause head loss? Branching, friction, velocity change. So if the branching happens in a channel, so obviously there will be energy dissipation. Friction increases, energy dissipation will increase. If some kind of bend is there, then energy dissipation will change. But if the velocity will change, then there is no energy loss as such. Right? Pressure difference will be there, but there is no energy loss. So it is the velocity change. Next. Find the loss of head when a pipe of diameter 200 mm is suddenly enlarged to a diameter 400 mm. The rate of flow of water through the pipe is this. So we will go back to the formulas in the second class or second lecture. So if you can see, so this is the factor that affect the head loss, right? Major head loss or minor head loss. So minor head loss, FD L by D is represented as K. Okay. So here is not the expansion is happening. So I will come to hydraulic diameter, or you can say that hydraulic diameter, how hydraulic diameter is defined, it is the 4 into cross-sectional area by wall parameter in contact, right? Okay. So you can see for a rectangular cross section, this is 4 into AB is the cross-sectional area and wall parameter in contact 2 into A plus B. So this is 2AB by A plus B for rectangular cross section, right? So this is for square cross section, this is for isosceles triangular cross section, and this is for circular annular cross section. Next, here is the minor head loss count. So now the flow is happening in a sudden expansion. So you can see that how this is represented. We have just seen that it is the U1 minus U2 whole square by 2G. So this can be written as 1 minus A1 by A2 whole square into U1 square by 2G, because A1 E1 equals to A2 U2, right? So for this case, K, your minor head loss term is represented like this. Next, when sudden flow contraction happens, what happens? This equation will change from previous one, you remember, to this. And now this Kc is represented as Ac by A2 when the sudden flow contraction happens. This is again the sudden flow contraction. And this is the choke contraction coefficient, and this is its expression when the entrance is rounded and if the entrance is not rounded. Okay, and this is how the choke number is also defined with respect to mean velocity. Okay, so these are the different shapes of contraction pipe, sudden contraction pipe, and how that affects your loss factor is written. So this is a loss factor coefficient are different for different cases. You can see the different Kc values, right? Like this. So loss of head in bed happens loss due to change of direction, loss due to friction, loss due to enlargement or contraction. So these are the expression for head loss in bend. Okay. Okay, now going back to this. So the loss of head when pipe diameter is suddenly enlarged, right? So first we will calculate the V1. First we'll calculate the V1 and V2. So flow rate is given, right? So V1 will be flow rate by A1, that is 0.25 by pi by 4, 0.2 square. It is coming as 7.96 meter per second. Next one is the V2, similarly 0.25 by pi by 4, 0.4 square equals to 1.99 meter per second. And now in case of sudden enlargement, we have seen the head loss. Head loss is V1 minus V2 square by 2g. We have seen in the earlier case, right here. So in the expression, if you put the values, what will come? It will be almost close to 1.816 meter. So the answer is B. Next. Depending on the inlet shape of sudden contraction and loss factor, what will be the choke contraction coefficient for following example? So you have seen in this, it is slightly rounded, right? So if you go back to the notes where the examples are given, where was that? Yeah. How is it? It is kind of like this, right? Option C, right? So it is 0.06 to 0.05 in between, right? So it is in between, that means it is almost around 0.05. Right? What was it? Yeah, it is 0.06 to 0.005 between. So it is 0.05, right? Option C. Next. What is the correct formula for loss at the exit of a pipe, where HL is the head loss at the exit of a pipe and V is the velocity? So correct formula for head loss, it is known as option D. So multiple time we have seen it is the V square by 2G. Next. Consider a fluid which is flowing in line through a flanked T. What will be the loss factor K? So here in this image, you have seen the flanked T, right? I think this is in the last lecture. Let me just see. See, this is for flanked T, 0.2. Option D. Next, head loss in branched pipe can be varied with what? It can be varied with branch diameter. It can be varied with, branch angle, diameter ratio, discharge ratio, all of the above. This is all of the above. Next, a 30 centimeter, you can see this, right? A 30 centimeter diameter pipe conveying water branches into two pipes of diameters 20 and 50 centimeter respectively. If the average velocity in the 30 centimeter diameter pipe is 2.5 meter per second, find the discharge in this pipe. Further, determine velocity in 15 centimeter pipe if the average velocity 20 centimeter diameter pipe is 2 meter per second. So find the discharge in this pipe, right? Discharge means Q, right? Q equals to AV. And discharge in the main pipe means it is talking about the one. So it will be Q1 into A1 into V1. So A1 is pi by 4, 30 centimeter, 0.3 square into 2.5. It is coming as 0.1766 meter cube per second. Okay. Next one is the determine the velocity in 15 centimeter pipe if the average velocity in 20 centimeter pipe is 2 meter per second. Now how will we calculate? So so in the pipe 2 we can calculate the diameter is known, velocity is known, so we can calculate its discharge. So it is A2V2 equals to pi by 4, 0.2 square into 2. So it is coming as 0.0628, right? It is 0.0628 meter cube per second. We know that from the junction we can say that Q1 equals, as 1 is breaking into 2 and 3, it is Q1 equals to Q2 plus Q3, right? So Q3 will be Q1 minus Q2. So Q1 we know, that is 0.1766 minus 0.0628 is equals to 0.1138 meter cube per second, right? And it has asked for the velocity V3, right? So now similar way we will calculate its diameter is 15, so it will be V3 equals to Q3 by A3. So it is, I think, 0.1138. 0.1138 divided by pi by 4 into 1.5, sorry, 0.5, 0.15 whole square, because it is in 50 centimeter. It is coming as 6.44 meter per second. Check this. Yeah. So it is option B. 0.17 is the first answer and 6.5, almost 6.5 is the second answer. It is option B. Right? Next question. Which formula is used to calculate the head loss in valves? K is the coefficient and U is the velocity of flow. So it is obviously option C, U square by 2G. What are the reasons for minor head losses in pipe? So it is basically valves and bends. For friction, it is always the major head loss. Generally, as the inclination angle theta of the valve plate increases, the loss coefficient also increases. Increasing the angle restricts the flow more, so it will lead to higher turbulence and higher energy loss. It is also increases. So increasing the angle, that means increasing the angle leads to increased restriction in flow. So that will increase the, again it will increase the energy loss. When two tanks with a water level differential H are connected by a pipeline, the exit velocity energy generally misplaced. This is true. Next, the efficiency of the pump is generally less than unity, because pump cannot produce all the energy given, right? So it is always less than unity. In ideal case, it is like it is equal, but in reality, it is always less than unity. Now we'll do some more questions. In a pipeline, how do frictional losses behave in laminar versus turbulent flow? So we have seen in the first chapter that frictional loss is proportional to U in case of laminar flow, and it is in velocity square in case of turbulent flow. So this is option B. So laminar flow, it is proportional to velocity, and for turbulent flow is proportional to velocity square. Next, what is the relationship between the fanning friction factor and the Darcy friction factor? So we have seen this in, so this is FD, Darcy friction factor is 4 times fanning friction factor, so obviously it is 1/4 of Darcy friction factor. Okay, option C. Not a square duct with For a square duct with side A, what is the hydraulic diameter? So we have seen hydraulic diameter is defined as 4 by weighted area by weighted perimeter. Like 4 into weighted area by weighted perimeter, right? So in case of square with side A, area is A square, right? And this perimeter is 4A, which is coming as A only. It is option B. Next. When a fluid flows into a large reservoir from a pipe, the loss is known as when a fluid flows into a large reservoir. So fluid is flowed into a large reservoir, right? So it is the exit loss where K tends to unity. It is the exit loss. Now some mathematical questions. Water flows through a 10-meter long circular pipe of diameter 0.05 meter at an average velocity of 2.5 meter per second. The Darcy factor is FD. Calculate the head loss. So we have derived that head loss is FD L by D into V square by 2. So this is 0.115. L is 10 by 0.05 into, 2G is there. Yeah. So if you confuse with the previous expression, what I have derived first, so there is a G in everywhere, okay? Or this unit will be like, this unit will be changed, okay? So here will be G everywhere. Okay, so everywhere there is a G. Or the unit will be different, otherwise it is same. Without G also you can write, but accordingly you have to change the head loss unit, then it is fine. Okay, so you can write in both way. I'm not writing again. You just remember the unit. Don't miss the unit. Unit is very important. So it is V square 2.5 by 2 into 9.8 equals to, so how much it is coming? 7.326. So it will be 2.5 whole square. It is 7.326 meter. This is the answer. Okay. Next. A pump sends water at 1 meter cube per minute through a 10 millimeter diameter conduit. The total static lift is 110 meter, 10 meter suction plus 100 meter discharge. The total head loss due to friction and fittings is calculated to be 10 to 10.84 meter. If the pump efficiency is 80%, calculate the shaft horsepower required. So before that, we will go through the last chapter. This is the simple equation of head loss. This is a major loss, this is a minor loss. So you can see head loss in pipes from 1 to 2 channel and to 1 to 3 channel. When the uh, when the channel is bifurcated. These are things that given in little bit detail. You can go through it. Okay, this is the K value. This is the K value for Cox. This is K value for other valves. Sure. So this is the total loss along a pipeline. So it is the summation of all the loss. So this is the total head curve and total head and load curve. So you can see so how the energy given to water per unit time LW is calculated as rho g QH, right? The problem is based on this concept. The Q is the volume of water which passes through a pump in unit time is called the pump discharge. And H is the energy which a pump gives water in a unit time per unit weight. The power Ls needed by a pump is called the shaft horsepower. This is defined as the Lw by Ls is the eta. Okay. The power is the Ls and shaft horsepower is defined as the eta. This is the load curve, this is the head curve. A is for the valve opening small and B is the curve, load curve for valve opening large. Okay. So we will come to this equation. LW rho G QH. So what is given in our case? So in our case there are multiple losses. First one is the static loss. Right? Then there comes the total head loss. Static loss is 100, 10. Right? 10 is for suction, 100 is for discharge, and total head loss is given 10.84. So summing this up, it will come as 120.84 meter. This is the total head loss, like total head. Next is flow rate. Flow rate is given as 1 meter cube per minute. So we need in seconds. So 1 by 60, it will be 0.016 0.0167 meter cube per second. Okay. Now we have to calculate the power, right? So water power equation we have seen in the, so water per unit time, it is given as LW. So LW is rho GQH. So for water it is 1000, G 9.81, Q is 0.0167, H is 120.84. So LW is coming as LW after calculation, it is coming as 19796.85. That it is power, right? So this is in watt. And we have to calculate the shaft power. So how the shaft power is defined? So it is LS by LW. No, it is LS LW sorry, I have missed something, I think. Yes, it is LW by LS into eta. It is shaft power. This is water power. Water power. And shaft power is defined as LW by LS equals to eta. So LS will be LW by eta. So it is, and eta is also given, the efficiency is given as 80%. So this will be 19796.85 divided by 0.8. It is coming as 24,746.068 watt. Okay, this is your answer. I've written it very badly. Let me write it clear. So your LS is 24746.068 watt. Okay, next. Water flows from a 50 millimeter diameter pipe into a 100 millimeter diameter pipe. The velocity in the 50 millimeter pipe is given. Calculate the head loss due to sudden expansion and the pressure rise across the expansion, assuming horizontal flow and neglecting pipe friction for this specific transition. So we have to calculate first the U2. So it will be coming from A1 V1 equals to A2 V2. So V2 will be A1 V1 by A2. So A1 is pi by 4, 0.50 millimeter means 0.05 whole square into V1 is 4 divided by pi by 4 into 0.1 whole square. So it will be cancelled out. So what it is coming? It is coming as 0.1 meter per second. Okay. The head loss due to expansion is given as U1 minus U2 whole square divided by 2g. So it is coming as 4 minus 1 whole square by 2 into g. Zero point 0.4587 meter. So this is the head loss due to sudden expansion. Next comes the pressure rise across the expansion. The pressure rise from the Bernoulli equations only. So from Bernoulli's equation I have done in the starting of the class. So if you remember the expression, so it is P1 by rho g, as it is a horizontal pipe, V1 square by 2g equals to P2 by rho g plus V2 square by 2g equals plus hd, right? So pressure rise will be defined as P1 minus P2. Pressure rise, so P2 minus P1 will be there. So P2 minus P1 by rho g equals to V1 square minus V2 square by 2g minus hd. So V1 we know, right? So V1 is 4. 4 square is 16 minus 1 by 2 into 9.81 minus hd is given as 0.4587. 0.4587. So delta P will be this into rho into g. So rho will be 1000 and g is 9.81. So it is coming as 3000.153 Pascal, right? So this is your pressure difference. across the pipe. Next, an air duct has a rectangular cross section of 300 mm by 600 mm. Okay. Air flows at a rate of 1.2 meter cube per second. Calculate the Reynolds number to determine if the flow is turbulent. Assume air density and dynamic viscosity like this. Okay. So for calculating the Reynolds number, we have to first calculate the exposed area, that is the hydraulic diameter of the air duct. So hydraulic diameter is given, hydraulic diameter is given as 4A by P. So for air duct 4, rectangular it has shade. So it is 0.3 into 0.6, right? And this will be 2 into 0.3 plus 0.6. So it is coming as 0.4 meter. Okay. Now flow rate is given, but we want to know the velocity, average velocity, right? So it will be V into Q by A. Q is 1.2 meter cube per second. Area is 0.3 into 0.6 equals to 6.67 meter per second. This is the velocity, right? So now we have every term of Reynolds number. So it is rho Vd by mu. Rho is given 1.2, V 6.67, D is the hydraulic diameter, that is 0.4, and mu is your 1.8 into 10 to the power minus 5. So how much it is coming? It is coming as 177,866.67, which is way more greater than the 4000 transitional value. So that is highly turbulent. So this flow is highly turbulent. Next, a pump draws water from a reservoir and discharges it at a point 15 meter higher. Okay. The pipe is 100 meter long with a 0.1 meter diameter. The flow rate is 0.02 meter cube per second. The system includes two 90-degree elbows and a fully open globe valve. If the Darcy friction factor is given like this, calculate the required pump power. It is mentioned that the friction that the system is 90-degree elbow, so there it is already defined. K is friction factor is 0.9. First we will calculate the velocity, average velocity. So area Q is, so average velocity is defined by 0.02 by pi by 4 0.1 square is equal to 2.547 2.547 meter per second. Now we can calculate the major loss, right? Because friction factor is given. Major loss friction factor is equation is Fd L by D V square by 2 G. So it is 0.02, L is 100 divided by 0.1 into 2.547 whole square divided by 2 into G. So it is coming as 6.6128. 6.61 meter. This is the major loss. How we calculate the minor loss? So minor loss, so it is the major loss. So here is the minor loss. So minor loss is coming from the elbow, two elbow, and that is that 0.9 each. 0.9 plus 0.9, and for valve that is 10. So it is coming as 11.8. Right? So, and this is the total friction factors. Sorry, this is the total K. So H minor will be summation of K, that is 11.8 into U square by 2G, that is 2.547 square by 2G. So it is coming as 3.91 meter. It is told that calculate the required pump power. So now total head is delta Z, because Z is there, right? The pump is in the different position, the inlet outlet in the different position. Then H major and H minor. So delta Z is 15. H major we have calculated 6.61 and 3.91. 6.61 plus 3.91, it is coming as 25.52 meter. Now the total power is P, or you can call it LW, is rho G Q into H. So for water, 1000 into 9.81 into Q is given as 0.02, and total head is 25.52. This head calculation is important because it controls major losses, minor losses, and also the delta Z, the height difference. So it will be 5007.024 watt. Okay. Next, a main pipeline splits into two branches at a junction. Okay. The main pipe has a velocity of 3 meter per second. One branch is at a 90-degree angle to the main flow. If the velocity in the 90-degree branch is 2 meter per second, calculate the head loss in the other branch. So from the lecture notes, you have known that if it is the 90-degree branching, that means K is 0.95, right? So we have calculated. So head loss will be, minor head loss will be 90-degree branch K is 0.9 or 0.95, we have seen, into U square, that is 2 square by 2G. So the expression is coming from minor loss into K into U square or V square by 2G. So it is coming as 0.183 meter. Okay. A duct has an oblong cross section formed by two parallel sides of length LP separated by a distance D. Okay. Now, with semicircular ends of diameter D, water flows through it at this. Find the hydraulic diameter. So there is a rectangle in the middle, right? So rectangle area is LP into D, that is 0.5 into 0.2, which is coming as 0.1 meter square. And there are two semicircles. No, there is one semicircle. No, there are two semicircles with semicircle ends, right? So two semicircles. So these two are making it. There are two parallel semicircles, so that making one. So area of that semicircle, two semicircles, is pi by 4 d square. This is the circle because we are considering two semicircles. So means one full circle. So it is coming as 0.0314 meter square. Yeah. So total area is summation of these two. 0.1314 meter square. Right? Now comes the weighted perimeter. This is the cross-sectional area, weighted cross-section. So weighted perimeter for two straight line is 2 into LP plus pi D, right? So 2 into LP will be 2 into 0.5 plus pi into D, that is 0.2. So it is coming as 1.628 meter. 1.628 meter, right? Now this is the hydraulic diameter. So hydraulic diameter DH is 4 into A by S. So 4 A is 0.0314 by 1.628. So it will be coming as 0.323 meter. Okay, this is your answer. Next. Water flows from a large tank into a pipe of diameter 0.1 meter. The velocity in the pipe is 3. If the coefficient of contraction is 0.62, calculate the health loss due to sudden contraction. Right? So, from the loss coefficient of this contraction, you can remember, I think, in the given case, it is given like in the notes, like minor in case of contraction, this is K is 1 by Cc, the coefficient of contraction, minus 1 whole square. So it is coming as 1 by 0.62 minus 1 whole square, which is 0.3756 or 0.375. Okay. Now this head loss at this point is K into U square by 2G. So it is 0.375 into 3 square by 2 into 9.81 equals to is coming as 0.172 meter. Next question. You need to pump oil from a storage tank to a processing unit 20 meter above the tank level. The pipe length is 500 meter, diameter is 0.2 meter, flow rate is given, friction factor is given, calculate the pressure the pump must deliver at its outlet. So it's the kind of problem we have done earlier, but still we have to do it. So the velocity is, I'm not writing the, I am writing only the expression. If you remember, you just put the values. So it is Q by M is pi by 4 D square. So Q is your 0.1 by 3.1 pi into D square. D is 0.2 whole square. It is 0. It is 3.18. Sorry. It is 3.18 meter per second. Okay. Now you can calculate the measured head loss, right? So it is Fd into L by D into V square by 2G. So it is 0.025 into 500 by 0.2 into 3.18 square by 2G. It is coming as 32.21. 32.21 meter, right? Now The total head will be this head HT plus delta Z. It will be plus 20. It will be 52.21 meter. Okay. The pressure head then will be delta P into rho G capital H. So oil density is 900 into 9.81 into 52.21. So it is coming as 4646099.991 0.25 Pascal. That is 460 kilopascal. Okay. A main pipe carries water at a velocity given. It splits into 90-degree branch pipe. The velocity of the water entering the branch pipe is this. If the pressure in the main pipe at the junction is given, calculate the pressure in the branch pipe just after the junction. Okay. Assume the branch and main are at the same elevation and neglect the pipe friction for this localized calculation. So, as this 90-degree concept is 90-degree branch pipe is there, so it is the K is 0.95. Earlier I have done with 0.9 I think, so please change the value of K from 0.9 to 0.95. Okay, so it will be coming almost close. Okay, so now the minor loss is coming K, that is 0.95 into U is given as 2.5 square because it is in the branch junction. So this is 2.5 square by 2G equals to is coming as 0.302 meter, right? Right? So if from the Bernoulli equation we know that P1 by rho G plus V1 square by 2G plus equals to P2, as there is no height difference, P2 square by 2G plus H minor, right? So now this pressure difference delta P is coming as, if you calculate you will understand, so it is V1 square minus V2 square by 2G. So V1 square is 4 square, right? 4 square minus V2 square by 2G, okay, minus the total head, that is 0.302. Just a minute. Right? Into rho is 1000 because it is water. So delta P is coming as 1912.38 Pascal, right? Then P1 is given, so P2 will be delta P2 minus P1 equals to delta P, right? So P2 will be this plus P1. So it will be plus 200 kilopascal. Okay. So it is 1.9 kilopascal. So plus 200 kilopascal. So it will be 201.9 kilopascal. Next. A pipeline with a diameter contains a fully open globe valve. If the flow rate of water is given, calculate the head loss caused specifically by the valve. Use the valve value K, right? So from first we have to calculate the U, that is U is Q by A. So it is coming as 2.83 meter per second. Then comes the valve loss, so head loss. So minor head loss K is 10 into 2.83 square by 2G. So it is coming as 4.08 meter. 4.08 meter answer. Next, a piping system has a 50-meter straight section of 0.05 meter diameter. Then it contains 90-degree elbows, each having a loss coefficient of K 0.9. Calculate the equivalent length of the two elbows and the total effective length of the pipe. So from the minor loss expression, you remember the equivalent length into K into D by FD. K is 0.9, D is 0.05 and FD is 0.02. So it is coming as 2.25 meter, right? Okay. Now for two elbows, the total equivalent length will be, for two elbows, it will be multiplied into 2, that will be 4.5 meter, and total effective length will be, so L total will be total straight length, that is 50 meter plus the elbow region. So it will be 50 plus 4.5, it will be 54.5 meter. Next. You need to pump water from a low-level reservoir to an overhead tank 25 meter above. The total length of the pipe is 150 meter. The flow rate is given. Total minor losses accounts for a sum is given. FD is given. Calculate the power required. First, you need to calculate the velocity. I will not do anymore because I have done this type of problems many times in this session. So you remember this coming for Q by A. So Q by A, Q is given as 0.015 meter cube, A pi by 4 d square, d is given 0.1 meter square. So it is coming as 1.91 meter per second. Tell me if the calculation is right or wrong, by checking by your own. Okay, I am just writing. So now for the measured heat loss, this is Fd into L by D into V square by 2G. So after putting value all these things, it is coming as 6.97 meter. Okay, and minor less is given as 5. So minor loss will be calculated will be Hm equals to K total V square by 2G. So it is coming as 0.93 meter. Okay. So total head loss will be the static head, that is the delta Z plus H major and H minor. It will be total 32.9 meter. Please tell me if the calculations are okay or not, and if you find it wrong, then do it by yourself. Okay. And the power required, so P is, and also the efficiency is given, so it is rho GQH by eta. So after putting all the values, you know rho G, that is for water, 1000, 9.81, Q is the 0.015, H is the final one, eta is the 0.75. It is coming as 6454.8 watt. Okay. Next, tell me if the calculations are correct or not. Okay. So here also the same kind of problem. The main pipe carries water. I think I have done this problem recently, right? Just check. Yeah, it is the same problem. It by mistake it has come again. This one is the, okay, these things I think it has been repeated again. Is it? Yeah, I think by mistake it has been repeated. Okay. So this is the same thing. So all the questions we have done. Okay. So I hope you have understood how the major losses and the minor losses are calculated due to major friction factors and the minor losses that is coming from your uh, veins, valves, sudden expansion, sudden contraction kind of thing. And please go through the lecture notes, which includes also some empirical equations of friction factor for both turbulent flow and laminar flow. Remember those, try to remember those at least, because those are the basic expression is same but little bit different, because it is based on the correction has been done over the years because of the experimental conditions, considering various experimental conditions. Okay, so I hope you find this helpful. Please go through the lectures on the YouTube, and if you have any question, please comment in the YouTube. Okay, we'll meet in the next week. Till then, goodbye.